This is part 6 of a series on recurrent neural networks. In this video, we'll look at one of the many variations of LSTM, Peephole LSTM. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the last 2 videos, we looked at long short-term memory, LSTM. We looked at the gate structure of LSTM and implemented it in code. In this video, we will look at the structure of Peephole LSTM and implement it in code. This is a traditional LSTM with peephole connections added. Felix A. Gers et al. Proposed Peephole LSTM, which adds peephole connections to traditional LSTM. In their 2000 paper, Recurrent Nets That Time and Count, and their 2002 paper, Learning Precise Timing with LSTM Recurrent Networks. Peephole connections allow the gates to utilize the previous cell state as well as the previous hidden state. Let's read the abstract of this paper. We find that LSTM augmented by peephole connections from its internal cells to its multiplicative gates can learn the fine distinction between sequences of spikes spaced either 50 or 49 time steps apart without the help of any short training exemplars. They showed that Peephole LSTM outperforms traditional LSTM in the task of classifying the intervals between spikes and input sequences consisting of sharp spikes. Now let's look at the structure of Peephole LSTM. In traditional LSTMs, the current input data xt and the previous hidden state ht-1 are input to each gate. And by this equation, ht-1 is hyperbolic tangent of ct-1 times ot. Therefore, we can see that the information of ct-1 is also input to each gate. However, if the output gate is closed, that is, if OT is 0, then the information of CT-1 cannot be input to each gate. Then each gate cannot receive any information from the previous state. Peephole LSTM solves this problem by adding peephole connections like this. The information of CT-1 is directly input to each gate through these connections. Even if the output gate is closed, information from the previous state can still be passed to each gate. The matrices PF, PO are also trainable parameters that are multiplied by CT-1 or CT, just like WF and RF. Each uppercase P is a lowercase p by P matrix, just like the matrix R. P is the number of hidden units. If we express these as formulas, they are as follows. CT-1.P is added to the forget gate and input gate. And CT-PO is added to the output gate. This improves the accessibility of memory contents and helps LSTM cells retain or discard information more effectively. This allows LSTMs to learn and capture long-term dependencies in sequence data. Now let's create a Peephole LSTM cell with Keras custom layer and implement a many-to-one model. Generate a time series dataset. This is the same as what we used in the LSTM model in the previous video. Let's generate 2 sine curves with different frequencies mixed with Gaussian noise as shown in the figure. Each curve consists of 1,000 data points. This figure shows only the last 100 data points out of 1,000. This data is a 1000 by 2 matrix. This data has two features, x1 and x2. Each column vector is a sine curve. In this figure, the blue curve is the time series x1, and the orange curve is the time series x2. Our goal is to predict each time series into the future. We use this data to construct a dataset for a many-to-one model. The number of time steps is set to 20, i.e. 20 time periods. The dataset looks like this. X-train has a 3D structure like this, and Y-train has a 2D structure like this. This dataset is for time series forecasting. Please refer to the first video in this series for how to construct this dataset. We are trying to create a Peephole LSTM model like this. This model consists of an input layer, a recurrent layer, and an output layer. The number of features is 2. So the number of neurons in the input layer is 2. Since we are going to predict the time series of each feature, we also have 2 target Y. Therefore, the number of neurons in the output layer is also 2. The number of neurons in the recurrent layer is set to 50. Since the number of time steps is 20, the recurrent layer is repeated 20 times. Now let's write a class for a Peephole LSTM cell using Gers custom layer. It takes as input the number of neurons. In a Peephole LSTM cell, there are 4 matrices W that are multiplied with the current input xt, and 4 matrices R that are multiplied with the previous hidden state H t-1. Additionally, there are 3 matrices P that are multiplied with the previous cell state C, t-1, and current cell state Ct. And there are also 4 bias matrices. We use Gers' dense layer to generate 4 Ws and 4 biases. And we generate 4 Rs. The biases are included in the W above, so we don't generate them again here. And we create 3 matrices P for peephole connections. We don't use biases here either. Each W in this dense layer is a 2x50 matrix. Each R in this dense layer is a 50x50 matrix. Each P in this dense layer is also a 50x50 matrix. 2 is the number of features in X that will be entered later. And 50 is the number of hidden neurons. The bias in this dense layer is a 1x50 matrix. These parameters are shared across all time steps. Next, we write a method to compute HT and CT, which will be passed on to the next time step. The inputs are the current data xt and the previous states H, t-1, and C, t-1. We use these formulas to compute the output of each gate as follows, and return HT and CT. Since WF is a dense layer, if you input X here, it will return the dot product of X and W plus B. Since RF and PF are also dense layers, inputting H and C here will return H.R and C.P respectively. The dense layer RF and PF have no biases. So this is equivalent to this expression. The outputs of other gates are computed in the same way. Next, we write the call method. This function takes data X as an input. If we unfold this network over 20 time steps, we get the following figure. H and C are initialized to 0 since there is no previous time step. Now to find H and C for each time step, we repeat the following procedure for a given number of time steps. We use the LSTM cell function written above to get H and C. H and C become the inputs for the next time step. At the end of the iteration, the final H is returned to be passed to the output layer. Since this is a many-to-one model, only the final output H is passed to the output layer. The final H contains all the information from the previous time steps. That is, it contains information about the sequence data from the past to the present. Now let's build a Peephole LSTM model. Create an input layer. The input layer will receive 3D data. The first dimension is the batch size of the data. The next dimension is 20, which is the number of time steps. And the last dimension is 2, which is the number of features in the input data. Next, we create a recurrent layer using the Peephole LSTM class we just created above. Initiate the Peephole LSTM class by entering the number of neurons, then feed X input into the class. This class returns the final H. Finally, we create an output layer. The number of neurons in the output layer is 2. The final output H of the recurrent layer is fed into the output layer. Here we use the linear activation function. This is because this model is for time series forecasting, so it's a regression problem. Create a model for training and compile it. And let's check the structure of this model. There is an input layer, a recurrent layer, and an output layer. The recurrent layer has 4 Ws, 4 Rs, 3 Ps, and 4 biases as trainable parameters. Each W is a 2x50 matrix, so it has 100 elements. Each R is a 50x50 matrix, so it has 2,500 elements. Each P is also a 50x50 matrix. And each gate has 50 biases. So the recurrent layer contains 80,100 parameters, which is the sum of the number of these elements. The output layer contains 102 parameters in W and B matrices. Therefore, this model contains a total of 18202 trainable parameters. Fit this model to the training data. The batch size of the data is set to 50. And the number of iterations is set to 50. And visually observe the history of the losses. Next, let's use this model to predict future time series. As we did with the LSTM model in the previous video, we predict future values for the next 50 periods. Let's just plot the time series for the last 100 periods of the original data. This has the last 100 data points. Iterate over 50 periods to predict the next 50 time series values. Predict the next value with the last n-step data points. If you feed the last n-step data points into this model, the output y-hat is the predicted value for the next time series. Append the predicted value to the last data array. In the next iteration, the predicted value is input along with the existing data points. If we repeat this 50 times, 50 predicted values will be appended to the last data array. The length of the last data array will be 150. The first 100 are past time series, and the last 50 are predicted future time series. P is the past time series, and F is the future time series. Now let's plot the past and future time series. Plot the past two time series in blue and red. And plot the two predicted future time series in green and orange. Let's check the results. You can see that the mean squared loss decreases significantly as training progresses. Now, let's look at the past and predicted future time series. The blue and red are the observed past time series. The green and orange are the predicted future time series. You can see that two sine curves with different frequencies are predicted. You can also see that the noise has been removed. Let's run this code. The results are as follows. Next, let's implement a many-to-many Peephole LSTM model. Import time-distributed class for many-to-many models. Generate a dataset for a many-to-many model. This data, like the previous code, consists of two sine curves with different frequencies. Xtrain has a 3D structure just like the previous code. But this time, Ytrain also has a 3D structure. This is because this is a dataset for a many-to-many model. Please refer to the second video in this series for how to construct this dataset. As with the many-to-one model, there is an input layer, a recurrent layer, and an output layer. However, unlike the many-to-one model, the output H of each time step is passed to the output layer. Let's upgrade our Peephole LSTM custom class for many-to-many use cases. We will use the return sequences argument to store the outputs from all time steps. If return sequences is false, only the output of the final time step is returned. This is used in many-to-one models. If return sequences is true, the outputs of all time steps are returned. This is used in many-to-many models. The code in this part is identical to the previous code, only the call method has changed. Now let's look at the call method. We initialize both H and C to 0. And we store them in two lists, H and C. During the iteration, we append the outputs HT and CT at each time step to the lists. If return sequences is true, it returns all HT stored in the list H. Convert the list H to a tensor. The shape of this tensor is 20, none, 50. 20 is the number of time steps, which is the number of iterations. None is the batch size of the input data X. And 50 is the number of hidden neurons. Convert this to a tensor of none, 20, 50 and return it. If return sequences is false, return only the last HT stored in the list H. When creating a recurrent layer, set the return sequences argument to true. This is because many-to-many models use all the outputs of each time step. And then we use the time-distributed class to create the output layer in this way. This means that the output layer is distributed across each time step like this. The rest of the code is the same as the many-to-one code. This model outputs multiple y-hats from all time steps. Therefore, when predicting the next time series value, only the final output is used. Let's check the results. The past time series and the predicted future time series are as follows. The results are similar to the previous code. Let's run this code. The results are as follows. So far, we have looked at the structure of Peephole LSTM and implemented many-to-one and many-to-many models for time series prediction. In the next video, we will look at the gated recurrent unit, GRU.